This is a lecture in Engineering, Computer Science 230, Computer Architecture and High-Tech Fundamentals. I am Professor Joseph Wunderlich. First we are going to talk about, this lecture is on number and character representations. Firstly, character representations. And here we have ASCII, which is for characters. This is a standard now. There have been others in the past, including EPSIDIC, used inside of IBM when I was there. Now number representations. So we do things in binary, base 2, because we're dealing with bits, charge stored on as a capacitance on a gate, the memory locations, and the ones and zeros, and then we process them through logic gates as ones and zeros. So we do things in binary, which is just 0 and 1. So here is a table relating typical base 10 numbers on the left to binary. So in binary you have count 0, 1, and you run out of digits and you got to toggle a 1. And at base 10 you count up to 9, you run out of digits, and toggle, you go to 0 and toggle, or you set the higher order number bit, or digit here in this case, not a bit, digit. In binary you run out of digits right away, and then you have to set the higher order number, and then you start counting again over here until you run out, and then you set a number. You start counting in both of these, both of these now, 0, 0, 0, 1, 1, 0, 1, 1, until you run out, and then you set another one. We also deal in hexadecimal in the computer, and that is just an easy way to represent the binary because it's a base 16, and you have when you run out of digits in hexadecimal, you have used all of the bits completely in a 4-bit, it's half of a byte. A byte is 8 bits. Half of a byte is called a nibble. And so these 4 bits represent F here in hexadecimal. We also have number representation where we alter this to or we use these bits in binary to represent different things. So we can have a sign magnitude here would be something to look at first, where you're just using this is the high order bit, the far left bit, to represent the negative numbers. So every place you see a negative there, you have 1 representing the negative. However, you'll learn in other courses, particularly EGR Computer Science 332 with me. If you take that course required for computer engineers and computer scientists, you'll see that two's complement lends itself to combining the arithmetic and logic hardware operations. So you have this representation here, and there's a process to create two's complement from a regular binary number. You complement all the bits and add 1. I'm not going to derive that here. It's something just be aware of that exists in this course. Now we want to convert a binary number to decimal. And so we have here 1111. And now this is the 0 numbered bit here. So you're counting 0, 1, 2 in reverse order. And the reason we do that is this is the 2 to the 0 bit. 1 times 2 to the 0. Anything raised to the 0 power is a 1. So that 1 there in binary represents a 1 in decimal. Then a 1 here, this is a 2 to the 1 bit. This is because this is the number 1 bit, 0, 1, 2. And this is the 2 to the 1 bit. That represents 2, because 2 to the 1 is 2, and you have a 1 there. And then a 1 there. This is the number 2 bit, so it's 2 to the 2, and which equals 4. And so if there's a 1 there, that means there's a 4 in decimal represented by that. You add them all together, and you get 7 in base 10. It's converting from a binary number to base 10. Now, to go from base 10 to binary, from base 10 to base 2, you lay out all the bits and you number them accordingly here in reverse order. So 0 here, the least significant bit, LSB, least significant bit, MSB, most significant bit. The LSB here, number 0 bit, represents 2 to 0, represents a 1. So if there's a 1 there, then that's going to be a 1. Now you're trying to figure out how to piece together, patch together pieces, ones in here scattered around that equal 9. Now you'll see what we end up with after we do that. We have 1, 0, 0, 1, which is 8 plus 1 equals 9. So after a while, you'll just know how to just look at that. But in the beginning, you want to do it like this. You want to say, well, if I put a 1 down here, you look, where can I put a 1? Find the biggest number that fits first. So what I mean by that is, from left to right, is like, these are all way bigger than 9. If I put a 1 there, I'm saying I'm converting, and it's 128 is, and this a 1 there would mean 128 in base 10 if I put a 1 in this binary. So it's not that. It's not 64. It's not 32. It's not 16. Now it's not 8 either, but 8 can be a part of it. And so there's not a 1 here, but perhaps there's a 1 here. So 8, yes, 1 here, put a 1 there. And now all I got to do is find the remaining part to cover. So I've covered part of it. And now if I put another 1 there, well, that's a 2. That would mean, or that's a 4, because 2 to the 2 is 4. That would mean if you have a 1, 1, that means I have 12. That's too big. So it should be 1, 0. What if I put a 1 there? Well, that would be 8 plus 2. That's 10. That's too big. So this should be 1, 0, 0. And then what if I put a 1 there? Yeah, there you go. So you got 8 plus 1. So 1, 0, 0, 1 is 8 plus 1 is 9. This is now floating point. So this is a homework problem that I gave a while back, whatever year that was, 2011, and I'll show how to convert. Now there's actually an example exercise in a couple of chapters ahead here, and you'll see that as an example. But here is homework. I asked them to convert all of these decimal numbers into floating point. This is binary floating point, BFP, and there's single and double precision, and also 1 and 0 and a trillion and a terabyte. And then there's some details in here, which I'd like you to read through on your own. More detail than I would quiz you on. This is IEEE floating point. Is the Institute of Electrical and Electronic Engineers setting standards. And so you'll have a sign bit, an exponent, and a mantissa you'll see in the examples here, and you put it all together. And you have ranges for floating point numbers. And special values for how to represent 0. Special operations and more details that you can look at later. Special things for infinity and special situations that we're not going to cover here, but there's the whole standard. And this references. This is part of the problem for solving, putting decimal numbers into binary floating point. What you see here is dealing with the fractional part on the right side of the decimal point. So what you do is you take, to get that into a binary number, you take that decimal point, that fractional part by itself without the number on the left-hand side of decimal point, and you multiply by 2, and you see what you get. And then you take, now part of what you get, you take the part on the left-hand side of the decimal point of the result when you multiply by 2, and that's the first binary digit that's going to be in the binary representation of the right-hand side of the decimal point. And then you take that number that you just got, in this case is 0.625, and then you multiply that by 2. You see what you get. If you have a 1 on the left side of the decimal point, that's going to be your second binary digit on the right side of the decimal point. Then you take just the 0.25, you don't take the 1 now, you take just the 0.25 from the right side of that last little product, that result, multiply that by 2, see what you get, in this case 0.5, there's a 0 on the left-hand part of that result, that 0 is your third digit on the right-hand side of the decimal point. And then I do it one more time here. Well, you don't know how many times you're going to do it until you run out of things on the right in the result. So you'll see 0.5 times 2, you get 1.0. So you take that 1, and that's going to be your fourth digit on the right side of the decimal point. And it's your last one because you've managed to keep multiplying by 2 until you just have a 0 on the right side of your result. And you're done. Now, the rest of this, the normalizing part, you probably want to wait until you'll see a lecture after this with an example that'll show you all the way to do this. Look ahead here to the next lecture. It'll be an example in detail. But for now, know that you've got to normalize this number. So you say, what do you mean? Well, I've got what's on the right-hand side of the decimal point. Well, how'd you figure out what's on the left-hand side of that decimal point when you're converting 1, 3, 1, 3? You know, that was on the left-hand side, the original number in decimal, and now I got to make that in the binary. Well, you do that you just do what we did in the previous example of patching it together until you've got something over there. So you got to start, way up on the left-hand side of high-order bits and make that number. So this is a little trickier when it's that big of a number. But anyway, you end up patching together now the left-hand and right-hand side, and you have a number in binary, but it's not normalized. So to normalize it, you've got to make it 1 point something. And to do that, you look at it and you say, well, originally it's just without any kind of power of 2 things stuck on the side, to make a scientific notation. So you've got to move that decimal point. Well, when you move the decimal point, you're moving it 10 parts over to the left to get it so it's 1 point something. Well, that's effectively making the number smaller. So you can't change the number when you change its representation, so you're going to multiply by 2 to the 10. It was 2 to the 0, right? It was the original number. It was what it is times 2 to the 0, which is just times 1. But now you're shifting over 10 points, 10 positions, so you're going to have to multiply by 2 to the 10 to keep it the same number. And then you end up with a normalized number. Now, when you have it normalized, the entire part on the right-hand side of that normalized number is called the mantissa. And then now the exponent, that 2 to the 10 thing, you have an exponent field that we need to deal with. And again, look to the example. You'll see what we're doing there. We're taking 10 plus 127. What's all that about? Well, that has to do with being able to represent a range of numbers from positive to negative. 2 to the negative 127 up to 2 to the positive 127, and so you're shifting the exponent around and packing it in. The formula for conversion has it built in, that 127. So wait till you do the next lecture ahead. Actually, the next lecture is just, you'll see in the guide, is just this particular sheet of paper. And then the one after that is the example. In the future, I'll perhaps switch them around a little bit. But this is all the details, or this is an example, a number of examples in here. So you just bear with it for a little bit and it'll make sense. And then you have a sign bit also. So we'll worry about that in a minute. Let's just look at the fractional part. You go down to the next example. You're converting 0.101565. And this is 32-bit floating point format, so you don't have so many bits for the Mantissa there. You'll see, and that's 64 would be a big long string. But anyway, you multiply by 2, you do the same process, get all those 0, 0, 0, 1, 1, 0, 1 that you're pulling out off of the results of that multiplying by 2. You keep doing the multiplying by 2 till you end up with a 0 on the right-hand side, and you're done. And that is your right-hand part. And then again, you normalize, and then you start sticking it into the form that we'll learn about in a second for the bit representation. And then a third example you can look at a little bit later on your own. Here are the answers, the solution to the homework problem above that I'd like you to come back and look at after we jump ahead here to not the next lecture, which is just a single page of the fractional part, but the lecture after that says floating point example. And then come back in here, and this will make more sense to you. But just to take a look at it here, what you're doing is you're getting, you have 1/4 in decimal on that first example solution, and you want to make that into some kind of power of 2. So the very first thing you do is you say, well, that's 1/2 to the 2, right? 1/4 is 1/2 to the 2. Well, 1/2 to the 2 is the same as 2 to the negative 2. And so you see this in the solution here. It's 1.0 times 2 to the negative 2, and that's called the normalized form. And that negative 2, even though that is the exponent, that is the real exponent, what you pack into the exponent field, you'll see 8 bits in the form below is your exponent field. You put something in there that is a result of a formula where you say negative 2 in this case equals e to the minus 127. That's the e minus 127 is the formula. And then you solve for e, and that e is what you stuff into the 8 bits for single precision binary floating point. And then what you have in the 23 bits there is your Mantissa field, which is everything on the right side of the decimal point for the normalized version of the 1.0. And the 1 is implied. The 1 is implied, so you'll see that in the example. So what I'd like you to do is come back and look at these today after we go ahead and take a look at the example coming up next. All these also. So these are all the problems that are assigned as this homework assignment. See, this is all part of the homework assignment that's up above here on the initial slide.